Welcome to this video, and in this video I want to have a look at one of the methods we can use for detecting exomoons. So an exomoon is a moon that is orbiting a exoplanet where the exo part basically means that it's around another star other than the solar system. So it's outside of our solar system around another star, and we're trying to find moons around exoplanets. So this particular method is looking at the asymmetric transit as a exoplanet passes in front of the star. It blocks out some of the light. It's a fairly straightforward method for detecting exoplanets. We've got like 5,000 now, but we don't have many exomoons. So we can actually look at this transit shape, and it will show asymmetric kind of shape in comparison to a single exoplanet. So normal exoplanet detection, it passes in front of the star. So as we look at it, we measure the brightness of the star or the flux coming from that star, and when the planet passes in front, it blocks out some of the light, and then it moves across, and then the star goes back to full brightness. And we can get the orbital parameters for that planet, we can get the size of the planet, because depending on how much light it blocks out, we can work out its radius and things like that. So it's a fairly good technique just by looking at how much light is blocked out by the planet. But you get a symmetrical transit when you do that. So the shape of that transit is symmetrical, like we've got there. Now, when we've got an exomoon, that moon will be orbiting a common centre of mass with an exoplanet. So because the exoplanet is normally much larger, or should be larger than the exomoon, then the centre of mass is generally closer to the exoplanet, but they're both orbiting this centre of mass, so they're going to kind of do this spiraling motion around the actual star. So the first thing is, you've got the system here with an exomoon and an exoplanet. They're orbiting a centre of mass. They are then orbiting around a star. So again, they make that kind of spiraling motion as they go around. Now, as we are looking at that particular star, the orientation of the exoplanet and the exomoon is going to be different each time. So the exoplanet and the exomoon are going to pass in front of the star in our line of sight. They block out some light, but each time that they do that, they're going to be in a slightly different orientation. So maybe the exoplanet will pass in front first, then the second time it might be the exomoon. Sometimes the exomoon might be actually in front of the exoplanet itself, so only the exoplanet is blocking out the light from the sun. So because they're orbiting themselves, or this common center of mass, and orbiting the star, they will transit slightly different each time round. So here we might have the exoplanet passing in front of the star first, followed by the exomoon, and that top transit shape there may show that, because actually on the right hand side, that's the first part that transits. So if you look at the x-axis, that's actually going to be time, and the exoplanet blocks out some of the light, and then as the exomoon follows, you have the combination of the exoplanet and the exomoon blocking out the light. So you get a little bit more light blocked out. As you can see, kind of at the back end of that transit, it dips down a little bit more, and it kind of lags a little bit. So it's not quite symmetrical anymore. Now, when it comes back round again, it could be in a different configuration. So maybe this time the exomoon leads, and then followed by the exoplanet. Now, if that happens, what will the transit look like? Well, it will block out a little bit of light first, and then it will block out a lot of light, because you've got the combination of the exoplanet and then the exomoon. And then the exomoon moves outside of line of sight, so it's just the exoplanet, and then it's essentially flipped the other way around this time. So you have the most light blocked out to start with, and then just the exoplanet. But the point is, each time that it transits, you get a slightly different pattern. So it deviates away from that symmetric pattern that you would get from just an exoplanet. And that can be an indication that there's an exomoon there. Now, it does have some drawbacks. An exomoon is typically quite small. It's going to be smaller than your exoplanet. We have found lots of exoplanets, but we haven't found that many small ones. So we haven't got that many that are Earth size or terrestrial size, because when they're small, they don't block out a lot of light. So the exoplanet itself will block out the most light, then the exomoon will block out a smaller amount, so it can be very difficult to see the exomoon, because the signal from that is generally quite weak, and the same reason why we don't have many Earth-sized planets. So it can be very tricky, and that is also assuming that this exomoon is Earth-size. chances are they're going to be smaller than that. So we're always going to struggle to actually see these. So again, going back to that transit with an exoplanet exomoon, you can see that the component from the exomoon is actually quite small, and you'd have to compare that, like it's going to be a deviation away from what the planet would do on its own. And you can see you've got some best fit lines there, and it's only slightly moving away from just the exoplanet. Now, this particular one was one of the main candidates, Kepler 1625b. There's a handful of candidates, none that are fully confirmed as being an exomoon yet, so we've still not got that many. But this was one of the main ones, and just to kind of demonstrate how hard they can be to find, is this was a Jupiter-sized planet with a potential Neptune-sized moon. So this is an enormous moon, and this still gave a fairly weak signal. So you can start to see how it's going to be very hard to find smaller moons. I mean, this is almost a gas giant in itself. Now, it's not confirmed, this particular one. It was a candidate. It's gone back and forth a few times. But this just highlights how difficult they can be to find with this particular technique. Now, there are various different techniques you can use to find the exomoon, and it's likely going to be that a combination of that is best to confirm if we have one there or not. So thank you for watching, and if you enjoy, you can check out some of the other videos.